representations for Euler equations of ideal hydrodynamics. Oleg, you are welcome. I want, okay.
Thank you, Semyonovich. Can you hear me? Is it okay?
Yeah,
Да, все прекрасно слышно.
Okay. So, my talk today is a continuation of a series of previous presentations dedicated to the application of methods from the theory of Lie pseudogroups to integrable partial differential equations. In this talk, integrability is understood as follows. A PDE is considered integrable if it admits a lax representation or, in other terms, admits a differential covering. Well, in my presentation that took place 1 year ago, in November of 2023, I discussed how the technique of twisted extensions of Lie-Reinhardt algebras can be used to construct a family of lax representations with non-removable parameters for the Euler equation of ideal hydrodynamics on a two-dimensional plane. Today, I am presenting generalizations of these results. Namely, I'll present lax representations for equations of ideal hydrodynamics on a two-dimensional Riemannian manifold and for the three-dimensional equations. So the talk will contain two parts. The first part is devoted to the Euler equation on a two-dimensional Riemannian manifold. This part is based on my recent paper in Journal of Geometry and Physics. Well, the dynamics of an unviscid incompressible fluid on a Riemannian manifold M is described by the Euler equations by this system, where system one, where the ball type V is the velocity vector of the fluid, P is the pressure, and nabla denotes the is the Levi-Civita connection on the manifold. Details can be found in, for example, in the book by Arnold and Hessen. I suppose that the density rho is equal to 1, so there is no, well, the density in the system 1 is not written explicitly. Well, we assume that dimension of the manifold is 2 and consider an open subset M in this manifold M such that this open subset has a trivial topology and there exist isothermal coordinates xy on this open subset M. That is, the Riemannian metric on M can be written in the following form for a smooth function h of xy. Details of the definition of isothermal coordinates and details about existence of isothermal coordinates can be found in the book of Postnikov. The case h identical equal to 0 corresponds to the plane geometry, to two-dimensional plane, and this case was considered first by Yang-Guan Charles Lie, where he, in the paper by Yang-Guan Charles Lie, he presented a lax representation without parameters, actually. And this result of Lie was generalized in my paper, in my recent paper, and well, it was the subject of the talk 1 year ago. Now I consider the case when h is not equal to 0 identically. In this case, the system 1 in the isothermal coordinates acquires the following form, the form 2. I can't see the last. Okay. Moment, just a second. Just a second. What is? Where u and v are components of the velocity vector, bolt type v. Okay. The third equation of the system implies the local existence of a stream function psi, such that the following conditions hold. U and V can be expressed in terms of this stream function psi. Upon using this substitution and excluding P from the first and the second equations of system 2 by the cross differentiation, we can substitute and differentiate the first equation with respect to y and the second equation with respect to x, and then the result will be the following. We obtain the Euler equation of dynamics of an inviscid incompressible fluid in the vorticity form. This equation, equation 3, where delta psi has the following form. It is the Laplace operator in the isothermal coordinates, and the Jacobi bracket, this bracket, is defined as follows. Okay, now, well, the natural setting for the Euler equation and its lax representations can be expressed in terms of the Poisson algebra P fracture, the algebra that consists of non-constant functions on a manifold, and this set is equipped with the Jacobi bracket 4. Once again, this Jacobi bracket. This Lie algebra, the Poisson algebra, is isomorphic to the Lie algebra of the area preserving vector fields. The map iota, defined as follows, maps the Poisson algebra to the Lie algebra denoted by H fracture or by these symbols. The algebra consists of the vector fields V capital, such that the Lie derivative of the Riemannian volume element, this to form, the Lie derivative of this to form is equal to 0. We employ the current Lie algebra P tilde, this Lie algebra consists of smooth functions of time t, taking values in the Lie algebra P. And this P tilde, this Lie algebra P tilde, is endowed with the pointwise bracket J capital. We consider the stream function psi and the pseudopotential Q below as the elements of this current Lie algebra P tilde. The Lie algebra H, the Lie algebra of Hamiltonian or area preserving vector fields, admits the extension by the outer derivation by the vector field W capital, where this vector is defined as follows. The Lie derivative of the Riemannian volume element with respect to this W is equal to the form eta itself. We can take this vector field W in the following form, where P capital and Q capital are any two functions that satisfy the following condition. Well, since the Lie algebra of area preserving vector fields and the Poisson algebra are isomorphic, we can the extension by the derivation W can be expressed in terms of the Poisson algebra, we have that the commutator of the vector field W with the image under the isomorphisms of the vector field of the function f. The commutator of these two vector fields has the following form, where E is operator, the differential operator, defined by the following formula. Well, remark, while the operator E is not uniquely defined, another choice of the functions P and Q, such that this condition holds, appends an inner derivation of the Lie algebra, of the Poisson Lie algebra, appends an inner derivation to the operator E capital. Okay, now we have the following result in terms of the above definitions. We have the following result. Equation 3. What is equation 3? This equation admits the family, the following family of the Lax representations, this family, where lambda is a parameter, f and g are arbitrary smooth functions of one variable, and the scaling of the pseudopotential Q allows one to assume either alpha is equal to 0, this alpha, or alpha is equal to 1. Furthermore, each of the following conditions 1 through 4 is sufficient for the parameter lambda to be non-removable. The following 4 conditions are sufficient to say that lambda is non-removable parameter. Either when alpha is equal to 1 and sorry.
I'm sorry. Please recall what is S.
Would you repeat it?
Please recall what is S in this.
S just means the argument of the functions.
Argument of the
Just argument of the functions.
Yeah.
We should substitute lambda in -1 in degree -1 here, and well, just to shorten the text. Okay, so these 4 conditions are sufficient for parameter lambda to be non-removable. Well, let me discuss the proof. The straightforward computation shows that equation 3 implies the compatibility of system 6. Moreover, when this condition holds, the compatibility of system 6 in its turn implies equation 3. In the first case, sometimes the Lax representation is called weak, and in the second, it is called perhaps strong. Okay. Now, to prove the second assertion, that the parameter lambda is non-removable, we notice that the scaling symmetry of the Euler equation does not admit a lift to a symmetry of equation 6. This means that if we write the system for the lifted symmetry, we obtain contradiction. So, once again, when one of the conditions 1 through 4 holds, the scaling symmetry of the Euler equation does not admit a lift to the symmetry to any symmetry of the covering system. Then the action of prolongation of the diffeomorphism defined by this vector field to the bundle of the third order jets, where equation 3 lives, maps where the system 6 lives, the covering system lives, maps equation 6 with lambda equal to 1 to the same equations, but with lambda equal to e to exponent of epsilon, this epsilon. In accordance with the observations in sections 3.2 and 3.6 of the paper by Krasильchik and Vinogradov, system 6 with the different constant values of lambda are not equivalent. That is, the parameter lambda is non-removable. Well, remark 2. Another choice of the functions p and q in the operator e. What are functions p and q? Let me recall. These functions p and q. They are not uniquely defined, as it was told. Well, another choice can be compensated by the change of the pseudopotential q. Indeed, if we take other functions p hat and q hat that enjoy the same condition, this condition, then the corresponding operator e acts as follows, or we can write it in this form, and furthermore we can write, it in this form where R is a function on our open subset M such that two following conditions hold. The existence of this function is guaranteed from the condition, these conditions that for sure are fulfilled because both p hat and q hat and p and q satisfy these conditions. So this function is function R exists, and the same consideration shows that this condition is fulfilled. Therefore, if we replace p by p hat and q by q hat in our covering equation, in our Lex presentation, this will be equivalent to the replacement of the pseudopotential as follows. Okay. Now, the next remark. While theorem 1 is proven by computations in isothermal coordinates, the forms of equation 3 and its Lex representation 4 actually do not depend on the choice of local coordinates on a Riemann manifold under consideration. So let me consider an example. Let's take the unit sphere in R3, or this manifold. And as it is, well, this manifold has two local systems of coordinates, the geographic coordinates phi theta, such that the following system is fulfilled. Phi and theta runs through these subsets. And the second coordinate system, the local stereographic coordinates, x small, y small, such that this condition took place. Well, the Euclidean metric on R3 can be reduced to the metric on the sphere, and the reduction in the geographic coordinates has the following form, while the reduction in the stereographic coordinates has the following form. From this formula, we see that the stereographic coordinates are isothermal, and the dynamics of an ideal fluid on the unit sphere can be described by equation 3 with the function h of the following form. So we substitute this function to system 6 and obtain the Lax representation where operator E has the following a bit complicated form. Well, let me recall what is system 6. This system. Okay. Likewise, we can use the geographic coordinates to write Euler equation on the sphere in the same form 3, where now the Lex operator has the following form and the Jacobi bracket has the following form. Then, when we rewrite the Lex representation 6 in the geographic coordinates, we can put operator E in the following form. Furthermore, we can we can simplify notations by considering new coordinates key that is equal to cosine of theta, and we obtain equation 3 and system 6, where the Laplace operator has the following form, and the Jacobi bracket has the following form, and the operator E, the operator that defines the extension of the Poisson algebra, has the following form. Well, remark 4. The Euler equation on a rotating sphere in the last coordinate system has the following form, where omega capital is the relative angular velocity. As it was shown by Platzman and discussed in the paper by Bichlo and Popovich, the last equation, this equation, is equivalent to the initial equation 3 or under a certain change of coordinates. So the Lax representation 6 actually can be written for the Euler equation on a rotating sphere, but well, let me skip the formulas. Okay, now part two. Sorry. Part 2, let me discuss the Lax representations for the three-dimensional Euler-Helmholtz equations. This part is based on my recent preprint in archive. Okay, consider the Lie algebra of vector fields on an open subset M in R3. We assume that this open subset has a trivial topology, and consider the Lie algebra of the volume preserving vector fields on this subset M. This vector field, this volume preserving vector fields, this Lie algebra consists of the vectors such that the Lie derivative of the volume element, this reform with respect to these vector fields, is equal to 0. Well, then, in terms of this Lie algebra, the three-dimensional Euler equations in the vorticity form, or also known as the three-dimensional Euler-Helmholtz equation, can be written in the following form, where now U capital, U bold type U is the following vector, and we consider it as an element of the current Lie algebra that corresponds to the Lie algebra of the volume preserving vector fields. Since this condition holds, the divergence of the vector field U is equal to 0. Equation 8, this equation, implies compatibility of the overdeterminate system 6. Well, two Lax representations for equation 7, sorry, were presented in the paper by Yangguan Li and Artyom Valentinovich Yurov. And well, the first Lax representation has the following form, where R is a function of t and x and y and z. The second Lax representation has the following form, where now Q is an element of the current Lie algebra that corresponds to the Lie algebra of all vector fields on M. Well, the parameter lambda in the following, in the system 9, actually is removable. Actually, when lambda is not equal to 0, the simple change of the pseudopotential, this change, transforms system 9 to the following form without a parameter. Well, the paper by Lee and Yurov does not discuss removability of parameter lambda in the Lax representation 10. And so, well, it was interesting to check this non-removability. And the theorem 2 states that actually the parameter lambda in system 10, sorry, it's a misprint, it should be 10 here. In this system, the parameter lambda in this system is non-removable. Well, the proof is the same as before. We take this scaling symmetry of equations 7 and 8. Yes, 7 and 8. What is 7 and 8? Ah, yes, okay. This equation 7 and 8 admit the scaling symmetry, but this symmetry does not admit a lift to a symmetry of system 10. Then we consider the prolongation of the diffeomorphism exponent tau s to the jets of the second order. And this prolongation maps system 10 to the same system with the parameter lambda replaced by the expression exponent tau multiplied by lambda. Well, again, we recall the observations from the paper by Krasильщик and Vinogradov and say that this fact guarantees non-removability of the parameter lambda in system 10. So we add some information, certain information for the about the system presented in the paper by Lee and Yurov. Now we have some generalizations. We have two more Lax representations for the three-dimensional Euler-Helmholtz equations, namely this system 11, with two parameters mu and lambda, and with Q being an element of the current algebra of Lie algebra of all vector fields on M. This system 11 provides a Lax representation for the three-dimensional Euler-Helmholtz equation. When mu, this parameter, is not equal to 0, the second parameter lambda is non-removable. The proof is well, the same. The straightforward computation show that equation 7, the Euler-Helmholtz equation, implies the compatibility of system 11. And the proof of the second assertion, that parameter lambda is non-removable, is similar to the proof of the previous theorem. Again, the scaling is does not admit a lift to the scaling of the Euler-Helmholtz equation. The symmetry of Euler-Helmholtz equation does not admit a lift to a symmetry of system 11. Well, now the second new Lax representation for the Euler-Helmholtz equation. This construction employs the outer derivation of the Lie algebra of the volume-preserving vector fields on the set M. As it was shown by Lichnerovich and Morimoto, The first adjoint cohomology group of this Lie algebra is one-dimensional, and it is generated by the cohomology class of the vector field W, such that this vector field W, the Lie derivative of the volume form with respect to this vector field W is equal to the volume form itself, the volume element itself. We can assume, we can put this vector field equal to this vector field, and we obtain the following theorem. System 12 with Q being an element of the current algebra of all vector fields on our subset M defines a Lax representation for the three-dimensional Euler-Helmholtz equation 7. The parameter lambda is non-removable in this system. The proof is the same as the proof of previous theorems, and one more fact is the following, that since the curl of Q is actually the element of the Lie algebra of volume preserving vector fields, while vector field W does not is not element of this Lie algebra. The summands that contain W in system 12 cannot be eliminated by any change of the pseudopotential Q. And the rest of the proof is similar to the proof of previous theorems. Okay, actually this is all that I can that I would like. Thank you for your attention.
Oleg, thanks a lot. Yes, thank you. My short question, well, in theorem 4, you have two parameters, mu and lambda.
Yeah.
Yeah?
Yeah.
And you say that lambda is non-removable, and what about mu?
The Q, the mu is just fixed number.
Yeah.
Without loss of generality, we can put mu equal to either 0 or 1. But by the scaling Q, we can scale the Q, we can scale the pseudopotential Q, the vector Q, and to replace mu by 1, and the same scaling by W, and then we get some lambda, and say the resulting lambda is non-removable.
Okay. Question? Sorry?
Sorry, I can't hear anything.
I would like to ask a question about the properties of the linear representation, like sphere.
Yeah.
Going back to the first part concerning the two-dimensional case.
Yeah.
Even in the case of plane, where h is equal to 0, what information can be extracted from the Lax pair? But because usually it's a Lax pair serves to reconstruct solutions, integrals of motion, and so on and so forth. For instance, it's probably I'm wrong, but as I remember from the book of Arnold about classical mechanics, that in two-dimensional, but in case of two-dimensional hydrodynamics, ideal one, there are infinite set of integrals of motion. Somehow, as I remember correctly, the densities are just curves, rotors of the vectors. Is it possible to extract the existence of such integrals in your approach, or probably it's just well known, I simply didn't follow? That's my question.
Well, my answer is the following. System 6 can be considered as the system that defines an infinite sequence of non-local conservation laws for equation 3. We can expand the pseudopotential Q in the series with respect to the non-removable parameter lambda. And for any choice of the functions f and g, actually, we can put them equal to, we take some concrete functions f and g, expand everything with respect to the parameter lambda, and obtain the series of non-local conservation laws for the Euler equation.
But local, as I remember, those conservation was density was completely local, just curves of the vector.
Yes,
The
sure, but
velocity,
this information can be extracted without any reference to the Lax representation. This Lax representation adds the following that we can.
But okay, but well, yes, of course. But okay, but only non-local conservation laws you can find the same from this Lax.
At this moment, yes, but well, perhaps in some future research, some more information, for example, some kind of restricted Bechdel transformations and so on, can be excluded, can be deduced from system 6. This is the work in progress.
Okay, and the second question would be how this type of Lax pair linear representation can be used for construction of solutions.
The answer is the same. It is well, for example, using some kind of restricted Bechdel transformations.
Restricted Bechdel transformations, not just from the analysis of the linear problem. Okay. Okay. Thank you.
Thank you for your question.
More questions? Okay, then again, thanks a lot for joining the seminar, and we'll meet in a couple of weeks again. Thanks a lot, and bye-bye.
Bye-bye.
Bye.